Question 5 begins by asking us for the systematic name of this compound. So the point about a systematic name is that, as it tells us in the question, there are lots of nitrogen chlorides, and what they'll differ in is the oxidation state of the nitrogen. So what you do with a systematic name is specify the oxidation state. So we've got that each of the chlorines will be -1, which is what chlorine will always be unless it's bonded to something more electronegative, like oxygen, in which case it could possibly be other things. But otherwise, chlorine is always going to be -1. And overall, the oxidation states must add up to 0 because it's a neutral compound. So if we've got -4 from the 4 chlorines, the nitrogens must add up to +4, but there are 2 of them, so it's 2 times +2. And that's what gives us our name. So the name of the compound is nitrogen 2, written as a Roman numeral, chloride. Okay, so that was the first bit. So next then we have to focus on this equilibrium. So it tells us that when you heat N2Cl4 up, it will reversibly break up into the elements like this. And the graph shows us what happens when we suddenly heat a sample up, and you can see that some of the N2Cl4 breaks up because the amount of it in the mixture decreases, but it doesn't decrease to 0, which tells you that you have an equilibrium where there's a bit of the stuff on both sides. So first it asks us how many moles of N2Cl4 there are at equilibrium. Okay, so that's our first job. So equilibrium is when the reaction has settled down and the concentrations have stopped changing. And so what's happened here is that the graph decreases and then it levels off. And it's that level at the end that's the equilibrium amount. So what we have to do is just read off carefully what that level is. And the number you read off the axis is 2.4. But what you've got to really be careful to notice is that, so always look carefully at the labels of the axes, because it's very common that the numbers will have been divided by some power of 10, and these have been divided by 10 to the -5. So that means that the actual concentration, or rather the actual number of moles at equilibrium, is 2.4 times 10 to the -5. Okay, so whatever factor they've been divided by, you have to then multiply by that number to get back to the original number. So that's the moles of N2Cl4 at equilibrium. Then it asks us what the equilibrium amount of N2 is. So what we've really got here is the same kind of problem that you've done a lot of. You had to read the data off a graph here, which is what made it a little bit more involved. But essentially you've done lots of these problems where, if you remember, what we said to do was to write down a table which has the equation across the top. So we have N2Cl4 going to N2 plus 2Cl2. And we said you should write down the initial moles and the equilibrium moles. And if we're talking about Kc rather than Kp, which is what we're doing here, the equilibrium concentration. So whenever you have an experiment where you know what you had at the beginning and then you have some information about what you have at the end, you should think about setting up a table like this. And that was really the key to this question, is just to have done enough practice that you think, yeah, I know how to do these problems, where I know what my initial composition is because it's just that. I've got 4 times 10 to the -5 moles of that, so I know what I've got at the beginning, and I know something about what I've got at equilibrium. I can set out the table, and that gives me everything. The more you practice, the more obvious to you it will be that that's the way to do it. So what we have initially is 4.0 times 10 to the minus 5 moles of N2Cl4, because that's our starting point here. And there was nothing else in the mixture, because when you read the question it just said when you take some N2Cl4 and heat it up, this is what happens. So there was no mention of any of this being there at the beginning, and that's because there wasn't any. So those are 0. At equilibrium, well, we've just read off that the moles of N2Cl4 at equilibrium was 2.4 times 10 to the minus 5. So we can write that in. And then remember, the key is that you look at the changes. So you say, right, this decreased. And how much did it decrease? Minus 1.6 times 10 to the minus 5. And the equation tells us that for every mole of that reacts, a mole of N2 will be formed. So if 1.6 times 10 to the minus 5 moles have reacted, 1.6 times 10 to the minus 5 moles of N2 will have formed. So this number therefore just becomes 1.6 times 10 to the minus 5. Now the chlorine, the equation again tells us that for every mole of nitrogen that's formed, you form 2 moles of chlorine. So the amount of chlorine is going to change by twice as much. So because that increased by 1.6 times 10 to the minus 5, this is going to increase by 2 times 1.6 times 10 to the minus 5, because of the 2 in the equation there, and that gives us 3.2 times 10 to the minus 5. Okay, so those are the equilibrium moles of each substance. So the answer for the question it asked was the moles of nitrogen is N2, but in the end you're going to need to know all of them. And then it wanted to know the equilibrium concentration of chlorine. So again, to work out the concentrations, you just divide by volume. So you get concentration is moles over volume in dm cubed. And it tells us that the sample has a volume of 100 cm cubed, which is 0.1. So it's the moles divided by 0.1 dm cubed. And if you divide by 0.1, that's the same as multiplying by 10. So these become 2.4 times 10 to the minus 4, 1.6 times 10 to the minus 4, and 3.2 times 10 to the minus 4. So now we have all the numbers we need to do the next bit, which is to find the value of Kc. So the Kc expression, remember the stuff on the right goes on the top, so it's the concentration of N2 times the concentration of Cl2 squared, okay, because that's a 2 squared in the expression, divided by the concentration of N2Cl4. So if we take the numbers for the equilibrium mixture, put them into that, we'll get Kc. So we've got 1.6 times 10 to the minus 4 times 3.2 times 10 to the minus 4 squared divided by 2.4 times 10 to the minus 4. So that's the calculation that we need to do, and that should give you 6.8 times 10 to the minus 8. Now that will have units, and remember that for Kc the easy way to do the units is to remember that if you let x equal moles on the right minus moles on the left in your equation, so in this case that would be 1 plus 2 is 3 on the right minus 1 on the left. If you let that equal x, then the units are just moles to the x dm to the 3x minus 3 So if you memorize that little recipe, then it's easy to get the units right. So we've got x is equal to 3 minus 1 is 2, so it's moles squared dm to the minus 6 is what you get for the units of Kc. And so that's your answer. The last part of the question is just applying Le Chatelier's principle to figure out what happens when you increase the pressure. So these are all gases, and what Le Chatelier says is that if you increase the pressure, the equilibrium will shift in the direction that will oppose that change. In other words, that will try to decrease the pressure again, and it will do that by moving in the direction where there are fewer moles of gas, because if there's less gas, there's less pressure. So what you say is that the equilibrium opposes a pressure increase, opposes a pressure increase by shifting in the direction where there are fewer moles of gas. And so, because there are 3 on the right and 1 on the left, that means it will shift to the left, and you can say that will shift in the backward direction. But the question actually asks what happens to the amount of N2Cl4, and obviously if it's shifted backwards, you get more of it, so the amount of N2Cl4 increases. And then the follow-up is, okay, so what happens to the value of Kc? And this is the classic trap that you just have to make sure you don't fall into. Remember that the only thing that changes the value of Kc is the temperature. And we haven't changed the temperature, we've changed the pressure. So all you have to say is that Kc is unchanged, because the temperature was not changed. The point is that the equilibrium had to shift in order to stay consistent with Kc. Kc was unchanging, but when you change the total pressure, because all the individual pressures change, the value of the expression won't equal Kc anymore until the equilibrium shifts, and then it returns to the same original value. So Kc is unchanged.